Okay, hi everyone. So today I'm going to talk about the transformation of a basis in continuous space. So let me give you a rough idea of what does it actually mean in physics when we talk about the transformation of a basis. This is amplitude over time. So let me do this side by side and show you this. La. Okay, so that's my last sound. How about instead of like recording my sound versus time, can I record my sound instead of the frequency? So when I say la, this is a sound composed of many different frequency coming from my mouth and my throat. Okay, so now you can see that my la sound, it is a pretty low pitch. So you can see there's a lot of like amplitude, a lot of sound coming from the frequency is lower than 1,000. But I also got a little high pitch, a little bit more at about, I don't know, seems like a 10,000 hertz, and there's like some 100,000 hertz. Those are probably my background voice. I don't think human being can make that sound. But essentially, this graph also describes last sound. But you can see that this function is not really instead of time anymore. It is instead of frequency. Okay, so this is an example of change of the basis. La is a sound, but in the time basis, it looks like this. In the frequency basis, it looks totally different. But if you get this information and put them together, they both represent the la sound. So this is what we call like there are two different representations for the same sound. Okay. Okay, so now let's talk about the whole idea in math. So what I just show you is a sound like a voice. So you hear me say la, but I can I can put this la sound in math by using wave function in the time. I can use this as a signal. Or I can record its frequency. The frequency, the sum of all the frequency coming out of my mouth, that can also help me to describe this la sound. Okay. And the time and the omega, they are kind of buddies because you can see exponential I omega t, they both contain the time information. So similarly, position and the moment and wave vector also has this power. It's exponential ikx. They both contain the spatial information. Okay, so I'm going to give you an example. All right, so to talk about the translate between the spaces, let me start from a finite dimension vector space. So remember that we're saying in a two-dimensional vector space, this is V, and I will need to use E1 and E2 to describe my V. I need two information, right? So I need to choose two bases. It can be E1, E2, it can be F1, F2. It can be anything, any two that's linearly independent. Okay, but how many information do I need? Like how many axis coordinate do I need to record such a wave? So this is an example where I am making a wave on a beat. So every beat is gonna go up and down, up and down. So x1, x2 is the first beat, second beat, third beat. And I'm calling it x just because it's, they're at different locations. And the psi of x is telling me the amplitude for each beat. So for example, the amplitude at x3 is called psi of x3. This x3 is not a vector here technically. It is it's a scalar. Right? It describes the wave at that's propagating in the x position. Okay, so how do I really describe this wave? One idea here, so this is a trick that we like to use when we want to discretize something. So when we treat the continuous, this is one of my common tricks. So first of all is that you can don't think about x as just one coordinate because there are n beat, right? So let me think about each bit is contain its own information. This one store a number 0, this one is 0, this one is psi of x3. So every bit store one information. So I can imagine this is an n. This is an n dimension vector where each spot store the message. So when I write x here, just because it's just a one random spot in my system, okay, I just sort of write the rules. So this is an n-dimension system, okay, so I can write it as a vector. Okay, now once it's become a vector, we can treat it like how we used to do it before for like 2D or 3D vector, right? Okay, so they can follow the same map. I can rewrite this one in a slightly more abstract way. So I can say, okay, this what it means is actually I have so much amplitude in this x1 coordinate. Okay. And I have so much of this amplitude in my x2 coordinate, and so on and so forth. Okay. So you can imagine that I am going to have, this is going to be a summation of a lot of amplitude at every coordinate. Okay, so so up to this point, I hope that you get the idea that x is not just one coordinate. This is not just a one-dimensional problem. This is actually an n-dimensional problem. Like we rethink about this, remodel this problem, and model it in this way. And the benefit of that is once we model in this way, then we can treat this guy from the linear algebra perspective. So that is very convenient. In case someone is interested in, so what is x1, x2, x3 specifically? So for example, what is x3? x3 is just 0, 0, 1, 0, 0, 0. It just means the coordinate at 3, at the third point, and so on and so forth. Yeah. Okay. So this side is really in the n-dimensional space, not just one dimension. Okay. And you can imagine that every vector, every like a coordinate we're choosing, they must be orthogonal. Orthogonal meaning they are perpendicular. Okay, so for example, I'm gonna give you an example here. So for example, 1 and 1, what's the overlap between 1 and 1? So we can calculate it, right? This one is 1, 0, 0, 0. This is 1, 0, 0, 0, 0. When you do the inner product, it will give you 1. Okay, so you see it's a unit vector. And then you can check if I try to do this, then I'll get, if I try to find out, what's the overlap between these two coordinates, then you can see it's 0, 1, 0, 0, 0, 0 for x2. And for x1, it will be 1, 0, 0, 0. So if you do the inner product, you will get 0 plus times 1 will be 0, 1 times 0 will be 0 again, so it will be 0. So that is saying that these two coordinates, if I and j are the same, then you get 1. If they are not the same, then you get 0. This is what we call orthonormal. So this is an orthonormal basis, which is great because it's like a very clean and there's a lot of nice property we can use. Here you see I'm using delta ij to exactly represent what I want, my idea. So this is a definition of delta. It's called the Kronecker delta function, okay, or Kronecker delta symbol, whatever it is. But essentially, it's saying if I and j are the same, you got 1. If they're different, you got 0. So now projection. For projection, so let's say if I have a wave and I want to know what is my amplitude as say x3 for this wave. How can I do that? So the way I can do it is I can just project that on my wave on this. So I can do this. And what does it mean?
let me show you. Okay, so x3 is, so this x3 is, let me give a different color and try it out here. So let's say I have a wave look like what I had here, 0, 0, 3, 4, okay, so on and so forth. And I want to know what is my psi of x3, which is 3, right? So how do I project, how do I get this number out, like in this more abstract symbol? So what I can do is that I can project my wave function on this coordinate, okay, to get my projection in that way. So how does it work? So x3 is 0, 0, 1, 0, 0, 0. And then here, this is a bra. Bra is a row vector, so it looks like this. And psi again is 0, 0, 3, 4, da, 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 da. So if you do the inner product for this two first, then you see 0 times 0, 0 times 0, 1 will take out this 3. So by doing this inner product, I can exactly get out this one. By doing, I can exactly grab my information at that coordinate, at x3, that coordinate, and then eventually this will be a number that will be 3 times my unit vector along 3. So just telling you, once you project it, you're along that direction. Okay, so that is the way to understand the projection operator. If you still get confused, you can make up some number and trying to convince yourself that it makes sense, in your way. So completeness meaning, if I project this, if I do my projection on not just 3, I can do my projection on everyone, right? I can do my projection on x1, and then do my projection on x2, x3, so on and so forth. If we sum them up, then I essentially just add up the whole thing, right? So like if I project my wave here, I will get some number in this coordinate, and then I'll get another number for this coordinate. If I add them up, I recover the entire same wave function. So that being said, if I do this projection for every coordinate, eventually I will recover myself. So this matrix eventually is going to be 1 because I just recover myself. So this is what we call the completeness rule. It's super, super useful when we are transforming bases from one to another. Okay. So now, if that makes sense, I'm going to come in to upgrade that question into infinite dimension. Okay. So infinite dimension is kind of like the bead, but now I have infinite bead. Okay. So I will have infinite bead. Okay. Let me try to. So how do we think about this infinite bead? We are going to take a nuanced way of doing the calculus. So what we're going to do is that we are going to cut out my string and pretend my string is a bead at every little segment. And all this bead between two beads, the size is we call dx. Okay, so it's just a really, really small, tiny segment that I cut out in my space. But this is one bead. Okay, one bead. So I can still call my first bead. I can still call this segment. Okay, I can still call that to be my first bead, and I will assign it to be one coordinate. Okay, so this is my axis x1, okay, or 1, okay, and this will be my axis 2. This is going to be my axis 3, and so on and so forth. So again, I will still have n, tons of like a segment. So I can still do this. Okay. But when I do this, I just will need to be careful because now my amplitude is not just, so for example, the psi for this one, for this beam, for the first one, the psi is not just psi of 1 anymore because it has a little width. So the total amplitude, the total phi that I got in this little segment is going to be psi 1 times delta x. and delta x is the size of this little b. Okay, so all of this are stored in the information of, let's say, 1 or x1. Let me do x1. So it's like it's more consistent with our notation before. But you kind of get the idea. I just need a way to name my system. Okay, and then I will do the same thing for the second bead, right? My second little bead or ribbon. And then so on and so forth. Okay, and I have to do it indefinitely. So I need to sum them up. And because I'm doing this cutting finally like a technique, so I am going to change my summation to be this, meaning I'm summing up an infinite of them. And then you can see it just naturally pop up like this. Okay, so the x here is essentially if you expand this integral, it's gonna be like this. X will become x1, x2, x3, a different x. It's not like you expand it, then it's still, like after you expand it, it will not be, after you expand this, it will be this, okay? It's not like, you know, when you expand it, it will not be just like this. It will not be all the same coordinate. This notation is slightly more confusing because in finite, it's easy to just say 1, 2, 3, 4, 5. But in continuous space, 1, 2, 3, 4, 5 is not really great because what we really want to say is that we are cutting it so smallly. So I just, you know, sort of borrow the idea that this 2 is really just x1 plus dx, like it's something really, really small, like its next neighbor. Okay, so that's how I come up with this. So this is how I project my wave function in a spaces called X. So it's gonna be an infinite dimension, and it will still possess this rule that if I am at the same coordinate, then I'll get 1. If it's different position, I will get 0. Okay. And because this now is a continuous stuff, so this will become a function instead of a number. Okay, it's just a same idea, but in different spaces. Okay, and then I also will have the completeness, relationship for this case. Okay, so that's the main idea of that. And in another video, I'll talk about how to apply this idea to do Fourier transformation.